The authors present a novel approach to machine learning by establishing a quantum dynamics framework, reformulating the iterative process of machine learning into a time-dependent partial differential equation. This is achieved by leveraging the Schrödinger equation and potential energy equivalence relationship, connecting quantum dynamics to thermodynamics through Wick rotation. The framework enables the investigation of machine learning iterations through quantum and mathematical theories. Machine learning is viewed as an optimization problem, akin to a kinetic process, drawing inspiration from the theory of dynamics, encompassing quantum dynamics, Newtonian dynamics, thermodynamics, electrodynamics, and molecular dynamics. The author's research explores the potential of a quantum dynamics framework for optimization problems, demonstrating the effectiveness of the Schrödinger equation in describing the iterative process of optimization algorithms. The diffusion probabilistic model has undergone rapid development and found extensive applications, exemplifying the successful application of kinetic theory to machine learning. The authors emphasize the importance of formulating kinetic equations that govern the learning process, and quantum dynamics offers a promising approach to machine learning, providing a rigorous theoretical foundation and potential support for quantum computer implementations. Machine learning has been reimagined through the lens of quantum dynamics, leveraging the probabilistic laws of motion captured by the Schrödinger equation. This alignment suggests that quantum dynamics can provide a robust framework for describing machine learning processes. Building upon the multiscale quantum harmonic oscillator algorithm introduced in 2013, significant theoretical and practical achievements have been made in functional optimization. The quantum dynamics framework, QDF, for optimization problems is founded on the Schrödinger equation, simplified by disregarding physical quantities and constants. This yields the quantum dynamic equation of optimization problem, equivalent to the constrained optimization problem. The QDF consists of several interconnected components. The potential energy and equivalent constrained optimization problem are linked through the state and ground state. The quantum harmonic oscillator is connected to the objective function, with optional locations. The free electron with drag term is equivalent to the Fokker-Planck equation, a diffusion equation. The sigmoid thermal dynamic equation is related to the Wick rotation, a mathematical concept used to connect different domains. Approximation methods play a crucial role in the QDF, including the classic approximation, Taylor zero-order approximation, Taylor first-order approximation, and Taylor second-order approximation. The two-level approximation and multi-level approximation are also employed. The energy superposition and softmax functions are used to approximate the objective function. By developing a quantum dynamics equation tailored for machine learning, the authors aim to establish a robust framework for describing machine learning processes, exploring the iterative process of machine learning through the lens of quantum dynamics. The quantum dynamics framework, QDF, formulates the time-dependent Schrödinger equation to model optimization problems, where the objective function is considered as the potential energy term. The equation is given by I partial differential psi, x, t, partial differential t equals, d squared, partial differential x squared plus v, x, psi, x, t, where d influences the system's kinetic energy, v, x, represents the bound potential energy, and psi, x, t, is the wave function. In the context of machine learning, the QDF represents the optimization objective as a potential energy term in the Schrödinger equation. The generalized objective function zeta, x, is introduced to formally represent the mathematical relationship of the objective function within the neural network's parameter space. This leads to the quantum dynamics equation for machine learning, given by I partial differential psi, x, t, partial differential t equals, d squared, partial differential x squared plus zeta, x, psi, x, t, which can be interpreted as a system of quantum-bound states defined by a potential energy function zeta, x. The modulus squared of the wave function, psi, x, t, squared, represents the probability distribution of finding the solution at a given point in time, according to Born's probabilistic interpretation. The Hamiltonian operator of the system is defined as h equals d squared, partial differential x squared plus zeta, x, where d determines the magnitude of the system's kinetic energy. The system can be annealed by gradually decreasing the value of d. The quantum dynamics equation of machine learning predicts two major iterative loops: the quantum annealing process, where the value of d is decreased, and the time evolution of the system towards the ground state under a fixed kinetic energy condition. This framework offers valuable insights from quantum physics, reinterpreting the optimal learning process in physical terms and mathematically converting the iterative process into rigorous time-dependent differential equations. The authors employed Taylor expansion of the generalized objective function zeta, x, in the machine learning parameter space to approximate the quantum dynamics equations, due to the analytical intractability of solving these equations. Initially, they consider the zeroth-order Taylor approximation of zeta, x, which reduces to zeta, x, equals 0 at the current position x0. This implies that the generalized objective function is undefined at x0, and the quantum dynamics equation simplifies to the free electron equation, as described by equation 6. This equation characterizes the quantum dynamics of an algorithm when the information about the generalized objective function is entirely unknown in the machine learning process. The free electron equation, which incorporates an imaginary unit to account for fluctuations beyond classical diffusion, manifests as a wave packet dispersion process, as illustrated in Figure 2. Subsequently, they consider the first-order Taylor approximation of zeta, x, given by zeta, x, approximately equals partial differential zeta, x0, partial differential x. The quantum dynamics equation for machine learning is then given by equation 7, which represents the gradient of the wave packet as the electron moves to the position x0, obtaining the current constraint potential zeta, x, as partial differential zeta, x0, partial differential x. This dynamic mirrors the algorithmic process of gradient descent optimization, where the optimization operation involves sampling the parameter space twice to estimate the slope of the generalized objective function at the position x0. Ultimately, the authors propose leveraging machine learning to approximate quantum dynamics equations, given the challenges of simulating wave packet dynamics in quantum mechanics using classical computers. The transformation of quantum dynamics equations into classical diffusion reaction equations via Wick's rotation enables tractable approximations on classical computational platforms. Specifically, the zeroth-order Taylor approximation of the generalized objective function, zeta, x, is shown to transform from the quantized free electron equation to the classical diffusion equation. This transformation leads to a degeneration of the dynamics from wave packet dispersion to a classical diffusion process, as illustrated in Figure 2. The Green's function for the unidimensional diffusion equation is a Gaussian function, describing the diffusion process of a point source. This classical diffusion process can be implemented in functional optimization problems using population Gaussian random walk sampling. The diffusion coefficient, d, influences the kinetic energy of the system and the standard deviation of the Gaussian sampling. Furthermore, the fundamental dynamical process of machine learning is revealed as a Gaussian stochastic diffusion process in the parameter space. After Wick's rotation, the first-order Taylor approximation of the generalized objective function, zeta, x, yields the Fokker-Planck equation. This equation describes the gradient descent process based on Gaussian sampling diffusion, allowing for the estimation of the derivative of zeta, x, through double sampling. The application of quantum dynamics theory in machine learning is discussed, focusing on the convergence analysis of the iterative process. The quantum dynamics equation is employed to analyze the convergence, describing the iterative process as a time evolutionary process. The general solution of the quantum dynamical equations is a superposition of states, indicating that upon measurement, the superposition will probabilistically collapse to one of the states. The energy levels and their corresponding states are crucial, with the ground state being the optimal solution. The process is likened to an annealing process, gradually reducing the kinetic energy, and a temporal evolution towards the ground state, similar to gradient descent. The Softmax and Sigmoid functions are also derived from the classical diffusion reaction equations, highlighting the connection between quantum dynamics and machine learning algorithms. The state of the system at time tau is represented by ck phi k, x, express, ek tau. where ck and phi k, x, are the coefficients and eigenfunctions, respectively, corresponding to the energy level ek. At tau equals 0, the system is in the state psi, x, 0, equals n Airy summation c phi I, x. As time evolves, the exponential term dominates, and states with higher energy decay more rapidly. The probability of a state with energy ek can be approximated as pek approximately equals express ek tau, n Airy summation express a tau, which represents a softmax function with respect to time. This function dynamically evolves with time, favoring states with lower energy. In a two-energy approximation, the system is simplified to two energies, A and E flat, where A is the low-energy state corresponding to the superior solution and E flat is the high-energy state corresponding to the inferior solution. The probability of the low-energy state A is given by P approximately equals 1 plus express EBEA tau, which is a time-dependent sigmoid function. The probability of selecting the low-energy state increases with time and approaches 1 as tau approaches infinity. The diffusion model, a machine learning algorithm based on thermodynamic theory, is interpreted in the context of quantum dynamics. The algorithm employs a Gaussian diffusion method, adding noise to an image and then denoising it to learn network parameters. The relationship between quantum dynamics and diffusion processes was initially explored by Anderson in 1975, who proposed the diffusion Monte Carlo (DMC) method for solving the ground state wave function of a molecule using a random walk. The DMC method is used to compute the ground state wave function of a quantum system by transforming an optimization problem into a quantum problem. The machine learning quantum dynamics equations are analyzed, revealing that the zeroth-order Taylor approximation of the generalized objective function requires the algorithm to sample the function in a Gaussian manner in the parameter space. However, the generalized objective function cannot be accurately defined in the same way as a function optimization problem, making direct Gaussian sampling in the parameter space impossible. The diffusion model in machine learning can be reinterpreted through the lens of quantum dynamics by approximating the learning space as a Gaussian sampling process in the parameter space. The Gaussian noise diffusion process in the learning space indirectly implements the Gaussian sampling diffusion process of the machine learning algorithm in the parameter space, resolving the limitation of direct Gaussian sampling in the parameter space. This alignment is depicted in Figure 4. Where the diffusion model's iterative process mirrors the theoretical framework of quantum dynamics in machine learning. Under the classical approximation of machine learning quantum dynamics, the diffusion model can be viewed as the zeroth and first-order iterative operations of the generalized objective function. In this context, each denoising iteration in the diffusion model is equivalent to a Gaussian sampling operation within the generalized parameter space. A sequence of one additive and denoising iteration for a sample can be seen as a sequence of Gaussian diffusion samples for a sample point within the parameter space. This novel interpretation bridges the gap between machine learning algorithms and quantum dynamics, providing a new perspective on the diffusion model. The diffusion model, depicted in Figure 5, effectively implements the Gaussian sampling diffusion process in the parameter space by eliminating the need to learn Gaussian noise. This establishes a mapping between the learning space and Gaussian sampling with gradient acquisition in the parameter space. The Gaussian sampling in the parameter space represents a classical approximation of the wave packet dispersion process in quantum kinetic theory. The quantum dynamics of machine learning suggest that the iterative process should involve an annealing process, which gradually reduces the kinetic energy. This implies incorporating noises with different standard deviations, from large to small, in the diffusion model may be necessary for system annealing. The efficacy of this approach is currently being experimentally demonstrated. The complete diffusion model comprises two iterative looping processes: the annealing process, involving reducing the standard deviation of Gaussian noise, and the diffusion evolution process. This paper establishes the quantum dynamics equation for the iterative process of machine learning based on Schrödinger's equation and relates it to the thermodynamics equation through Wick rotation. The quantum dynamics equation is used to obtain the basic iterative process of machine learning through Wick rotation and Taylor approximation. The generalized solution of the equation is then used to obtain the softmax and sigmoid functions commonly used in machine learning, providing a physical and statistical explanation of their significance. The convergence of quantum dynamics frameworks for optimization algorithms is a topic of significant interest in recent research. Quantum annealing, deep unsupervised learning using non-equilibrium thermodynamics, and score-based generative modeling through stochastic differential equations are key areas of study. Multi-scale quantum harmonic oscillator optimization algorithms and their applications are also explored.